this is equal to 4.5 divided by 2.250 times 10 to the power 3 Newton. Okay, then we do summation about forces in the x direction is equal to 0. So we have 7.794. So minus 7.794 times 10 to the power 3 plus bx. So from here, bx is equal to 7.794 times 10 to the power 3 Newton. Okay, and the direction is correct. This one is going this way, and this ones are going up. So now what I'm going to do is I'm now going to sketch where the position of elements are elements H and K are. Okay, so where I'm going to draw this line. Okay, now I'm also going to draw the centroid. Okay, so this is also different color. So this is also our centroid. So over here, this is our element K. Over here, this is our element H. Okay. So now we are going to do this, okay, by focusing on two methods. Okay. And both methods, the answer will be the same. Okay. So what I'm going to do now is I'm going to use method number one. So method number one does not use static analysis at all. Okay, method number one, we did not use static analysis. Okay, so let's look at method number one. And the answer will be the same whether you use method number one or two. So method number one. Okay. Okay, so method number one, I'll write down here without using static analysis. Okay, and I'm going to consider, I'm going to draw this, take this diagram with me. Okay, I'm going to copy and I'm going to paste as an image. Right. So relative to this image over here, which we'll use, right? Relative to the elements, this is known as the left-hand side. Okay? On the right, relative to the elements, this is going to be known as the right-hand side. Okay. So I'm going to analyze based on the left-hand side. Okay, so I'm going to look at the left-hand side. So left-hand side means I'm going to sketch this out. Where this is your AY. And this is going to be your 4.5. Right? Why is that? Okay. Okay, so where that is equal to 4.5 times 10 to the power 3. Okay. And this line is where you have your element K and element H. Okay. So what I'm going to do now is I'm going to AY, we know that AY is equal to 225. Is equal to, wait, is equal to what is AY is equal to? Now I forget what is my AY. AY is equal to, we just did that. 2.25. Okay, 2.25 times 10 to the power 3. Okay. So the moment, right, is equal to 2.25. So moment, so you might ask Eugene, moment away. Moment at the element, right? So I'm going to assume positive is going anti-clockwise. Okay. So moment will be equal to the 2.25 is going to be minus, right? And the distance is what? So if we were to look at the distance, is equal to 6, is equal to, down here 60, over here from here to here is 20. Okay, so let me put in the dimension. This is 80 millimeters and this is 20 millimeters. Okay, relative to the element, right? So multiply by 0.08. Okay, and then we have what? We have plus, right? Because now relative at the elements plus 4.5 times 10 to the power 3, right? Multiply by 0.02. Okay. So now this is equal to minus 2.25 power 3 times by 0.08. It's going to minus 180 plus by 4.5 multiplied by 2 multiplied 0.02 plus 190. So now this will be equal to minus 90 Newton meter. Okay. So when it's minus, okay, what does it means? Okay, it means the AY, this AY that's inducing a minus, the load is higher, right? So the moment about Z is in this direction. So when that's the case, right, because the AY is generating a higher moment, the 4.5 is generating less. So the MZ will be in this direction, right? So when that's the case, this will be under compression. And over here, this will be under tensile. Okay. So now this is by using, let me clear this up. This is by using the left hand side. And likewise, we have a load over here, which is equal to what? Which is equal to 7.794. And it does not matter in a sense that we know that the load in the x direction will be equal to minus 7.794 times 10 to the power 3. We put minus over here because this is for what? Compression. Okay. So you can also write this as 90 Newton meter and is going in this direction. Okay. Now, if we now use method number 1 without using static analysis, we now look at the right-hand side. So the answer should be the same, right? So you look at the right-hand side, right? You only have one load now. Now this is your what? Your By. And then we know that we have a perpendicular distance. And the perpendicular distance over here is equal to 60 millimeters. And we know that we have a Bx over here. We have a Bx over here, which is also equal to 7.794 times 10 to the power 3. So over here is our elements, right? So our element K and our element H. right? So we know now, again, it's up to you, okay? So I'm going to now take anti-clockwise as positive, right? So the moment now will be equal to what? By, which is equal to 2.25 times 10 to the power 3 multiplied by a distance. Let me check. I don't think it's 0.6. The distance is not 0.6 because this is 40 millimeters. Okay, I do apologize. So this is 40 millimeters now. Okay, so 2.25 times by 0.04. This will be equal to 2.25 times by 0.04 is equal to 90 Newton meter, and it's going positive in this way. So over here, this is the direction. So this is compression. This is tensile. And then what we have, our px, because it's pushing into the elements, is also equal to minus 7.794 times 10 to the power 3 Newton. Okay. So whether you use the left-hand side or right-hand side, your answer will always be the same. Okay. Now, method number 2 is using static analysis. What we are doing is basically, you can say we're calculating the reaction. Okay. So now let's look at method number 2. Now, either method you use, you decide, okay, which one you're more comfortable is entirely up to you. But method number 2, you must know what is a positive shear and what is a positive, sorry, what direction is a positive bending moment analysis, okay, which I will show you now. Okay, so method number 2, we are going to use static analysis. Okay, watch this now. So we know, and now we are going to look at the left hand side. Okay, so this is our AY. This will be our 4.5. And then we have our elements. Okay, element H or element K and your element H. Okay, and we also have a we have a and this will be equal to 7.794. Okay, now because over here is where our element is now. Okay, remember I told you all the moment cannot be in the what, in the object, right? So this is basically over here, this is going towards the right. So we are analyzing. So what is available is the material on the left hand side. Okay, so when you have material on the left hand side, this is the positive shear or positive bending moment assumption. Okay, so moment, I just call this moment. Did I call it a name? I just call it moment. Okay, if we have later on, the shear will be coming down in this direction. But we're not dealing with shear yet. Okay, let's focus on moment because the moment will generate our normal stresses. Okay, so if we look at our moment, so now if we go to take moment from this point, right? So we are going to say that summation about moment Z is equal to 0, right? So we have AY is equal to minus 2.25 times 10 to the power 3 multiplied by a distance of 0.08. Then the next one is plus 4.5 times 10 to the power 3 multiplied by a distance of 0.02. Okay, let me shift this a bit. And then, so we are taking this moment at this dot over here. The moment M is plus M, the whole thing will be equal to 0. So therefore, M will be equal to positive 180 minus by 90. This is equal to 90 Newton meter. When it's 19 Newton meter, it means that it's positive, means the assumption is correct. So up here is compression, down here is tensile. Okay, so if we compare the two methods, it's the same answer, compression and tension. Compression and tension. Okay, now if we were to do with the right hand side, okay, now I want you to take note about this arrow. Yeah, I want you to take note about this arrow. What happened when we go to the right hand side? So now if we now were to do this on the, now I'm going to write this further. We know that the px is also equal to what? Is equal to, so because we have a px over here, okay, so we know that the p is also equal to what? 7 point. And by looking at the direction,